D10, Kepler's third law. Now we're going to go back to the early days where this was the pressing problem to understand Kepler's third law. And I'm going to show you a beautiful derivation where we're going to actually derive the law from Newton's law of universal gravitation and his F equals ma equation. So what we're going to need F equals ma, which we already have talked about, and 2, we're going to need the universal law of gravity, which we already have covered most recently. And we're going to need the acceleration formula for movement in a circular path, v squared over r. This is what we're going to need. Now, what Kepler showed by measurements of the time it took planets to go around the sun and the distance from the sun to the planets. Now, the planets go in close to circular orbits, but not quite. They're actually a little bit elliptical. And when we have the elliptical orbit, we use what we call here the semi-major axis. So the major axis of an ellipse, say if this is the major axis, you would take half of that to get your semi-major axis. And we're going to just approximate everything as a sphere is close enough, since the amount of ovalness is very, very small for the planets. We call that the eccentricity. We'll be studying eccentricity in more detail later. So when you take, for say, Mercury, Venus, Earth, Mars, Jupiter, Saturn, the planets that they knew at the time, you take the semi-major axis, which is going to be the r, you take the r, the radius, and you take the period, you find that r cubed over the period squared is equal to a constant. Kepler's third law. So let's see if we can derive this mysterious law that was discovered by Kepler from first principles using the laws of motion and gravitation and the formula for the acceleration where we're in a circular path. So we write down F equals ma and apply it. The force is going to be G, M. Now m's the mass of the sun, and this mass is the mass of the planet, over r squared. And that's going to equal mass times acceleration, which is v squared over r. Now remember that when you go in a circular motion, the velocity is 2 pi r divided by the period. So that means we have the equation gmm over r squared equals m. We put in for the v. We're going to have an r down there, but the v is all this stuff. 2 pi r over t, all that squared. So now we can see that this m cancels. Doesn't matter what the planet's mass is. So we'll have g big M over r squared. So this will equal to 1 over r. And then what do we have here? Well, 2 squared is 4, pi squared, and then there'll be an r squared here, and over a t squared. And we can see that we're going to have a cancellation of one of the r's. So this will be 4 pi squared r over t squared. And now look, when you bring that r, see, over here you can get an r cubed. This is amazing. And a t squared is popped down. This is amazing that these equations are coming up with this derivation of Kepler's third law. So let's go ahead and write this t squared on the other side. Multiply both sides by t squared, so the t squared comes over here. Multiply both sides by the r squared, so we take the r squared to the other side. 4 pi r cubed. Brilliant. Look at that. T squared r cubed. So now we're going to multiply by t squared. And we're going to find gm t squared over r squared is equal to 4 pi squared r. And now look at this. We're getting closer. The r cube's going to appear. The t squared's appearing. So we have gm t squared is 4 pi squared r cubed. Very, very nice. So now we can find r cubed over t squared by bringing the t squared down here. We're going to get gm divided by 4 pi squared. Now this is remarkable. Not only do we have the relationship, but we also have the constant. And in the next section, I'm going to talk about finding that constant.